So welcome to Math 331, problem solving. This is lecture 29. So we are getting very close to the Putnam. So you should all feel excited. You will have the hardest exam in the history of Williams College and the most generously curved exam in the history of Williams College. So for at least the next couple of classes, I want to just talk about some of the Putnam problems as well as some of the problems that I think are just fun and accessible. So we had listed 5 possibilities from the A1 problems, and we've already done some of them. So we've already done the one from 1989, and I think we did the one from 1994 by basically just looking in dyadic intervals and just grouping things. So we did that one. So we've got a couple of ones left to do, and we did 17. So we've got basically for which positive integer n, when we have fn as a product of cosines, you'll find the smallest n such that the second derivative at 0 is at least 2023. And then we have the basketball star Chanel O'Keefe, which is a very famous fun problem. So we should have time to do both of them today. So if anybody has a preference for the order in which we do them. So first voice wins. To the second one, okay. And so my son has actually met the person for whom this is named after. Okay. And so let's try to paste this. Okay. So Chanel starts off shooting below 80%, and eventually by the end of the season has improved to shooting above 80%. Was there necessarily a moment in time when Chanel was shooting exactly 80%? So in problems like this, you always want to figure out which numbers matter. Well, there's only one number, 80%. And we know at some point it was less than 80, some point it was greater than 80. So the question is this true no matter what, or is something special about 80? So you think it holds for any p? And if so, can you give me maybe a sequence? So give me another probability. 60%. So let's consider 60%. So eventually, she has to be shooting above 60, and at some point she's below 60. All right. When you hear 60%, how do you think of that? 3/5. So I want to look at hits and misses. So she starts off below. So maybe she starts off, miss, 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 hit, hit. Right? What percent are we at? We're at 40%, 50%, and now we're at 4/7. Is 4/7 the same as 3/5? No, I don't care what it is. I just know it's not. What about 5/8? Is that 60%? No. What's the simplest way to know that 5/8 is not the same as 3/5? So how do you know 5/8 is not the same as 3/5? So they're both reduced. We've removed all common factors, right? So since we've written them as an irreducible fraction, they can't be the same. So for the next one, 1, 2, 3, 4. Now I'm at 6/9, which is 2/3, which is clearly above 60%. So here's an example of a string where I start below 60% and I end above 60%. So this shows it's not true for all p. So if it's going to be true for 80%, 80% has to be a somewhat special number. So we could start playing with some sequences to get some feel for the problem. We could start off with, maybe, some misses in the beginning. And now this was doing, 60%. Let's try to do 80% or 4/5. And now let's see what happens as we put in hits. So at this point, we've got 4/7, that's too small, 5/8, too small, 6/9, 2/3, which is too small, 7/10, too small, 8/11, that's clearly less than 80%. Now we're at 9/12, which is 3/4, too small. So now we're at 10/13. So 10/13 versus 4/5. So that's 50 versus, so it's clearly going to go in this way. So 10/13 is too small. This would now be 11/14 versus 4/5. So that'd be 55 versus 56. So it's too small. And then the next one is going to give us 12/15, which is 4/5. Now, this is not a proof, but this at least shows us with this one sequence that it's at least possible, right? So you've got one data point. Do you think it will always be the case that you hit 80% exactly? You could start off with, say, 79 out of 102, and you start playing the games there and see what's going to happen. And in the interest of time, it works. So you can try a bunch of cases that are always going to work. So at this point, you're beginning to feel I should maybe be trying to prove it. So this is a very nice problem in which they write, was there necessarily, well, let me highlight that because it's was there necessarily a moment? So it's not telling you the answer. It's not telling you what to prove. So it's not a bad idea to spend some time, gather some data, get a feel. Do you think that this is the case? What is the difference between 3/5 and 4/5? I'm sorry? 1/5. But what other numbers do you think might work? 4/5 at least worked in this case. 3/5 did not. So 80%, we can write this as 4/5. Maybe we can write this as A/B. What's the relationship? For which A and B is this going to be the case? That's a more general result than they're asking here. They're asking for 80%, but the more general problem is for which fractions A and B will this hold? Okay, so let's continue. And then we can think a little bit about what's going to happen. For a lot of situations, I can rearrange all the shots in the beginning until I get to the point where I'm about to break 80%. It doesn't really matter. At some point, I'm less than 80%, and then at some point, I'm greater than 80%. This is not a continuous problem. So I can't use the intermediate value theorem to say there must be some moment in time when I hit 80% because things are discrete. But there has to be a specific shot where she goes from below 80% to either 80% or above. So assume on shot N, go from below 80% to above 80%. Do I need to worry about what would happen if she hit exactly 80%? No, because then I would have solved the problem. We're trying to show that no such n exists. Must show no such n exists, because if no such n exists, then the only possibility is she had to hit 80% exactly. She can't go from below 80 to above 80. So is everybody comfortable with this? So what must have been true a moment before? It was below. So how should we write what she was?
Plus 10 minus 1 over 8 plus 7 minus 1.
Well, we know. So here's, where we are at shot n. And we now have shot n plus 1. And the percentage is greater than 80%. And the percentage is less than 80%. So Oh, I'm sorry. It was assuming it goes at short n, so that should be, I think, n-1, and n, I think the way I chose to normalize things. No. This was right. At short n, she was below 80%, and then short n+1, she was above. So what's the denominator at short n?
B plus N.
I'm sorry?
B plus N.
Well, we're doing 80%.
That's fourth.
No. So at short n, so right before she shoots, how many shots has she made? How many shots has she attempted before she shoots? Before the nth shot, how many shots has she taken? n-1. So she has n-1 shots done at this point. And she's hit how many? Let's call it h. And then after she takes the next shot, how many shots has she taken? She's taken n shots, and how many has she hit? h+1. And so I could write this really pedantically as n-1 plus 1 h+1 to emphasize that she took one more shot and made it. And what do we know about these fractions? So what do we know about these two fractions?
One is less than 4/5.
One is less than 4/5, is less than 4/5, is less than h+1 over n. And again, you could more generally do this as a over b and try to figure out which a and b would work. We'll do 4/5 for now. When I see something like this, the most natural thing for me to do is like cross multiply and whatnot. So I would get from this 5h is less than 4n minus 4 from the first, and 4n is less than 5h plus 5. Let me just get the 4n's on the same side and I can isolate it. So I'm going to get 5h plus 4 is less than 4n is less than 5h plus 5. And these are strict less thans. So what's the problem? There is no integer between two adjacent integers. So these are adjacent. Impossible. So she can't have gone from below 80% to above 80% without having gone through. If we wanted to now generalize this and do a over b, it shouldn't hopefully be too bad. So we would have h over n-1 is less than a over b is less than h plus 1 over n. So we'd get bh is less than an minus a, and then we would get an is less than bh plus b. So we would have bh plus a is less than an is less than bh plus b. And so we want these two to be adjacent. So when are they going to be adjacent?
When there's a difference of 1.
When there's a difference of 1. So a equals b minus 1% is going to be b minus 1 over b. That's how you should view 4/5. 4/5 is really 5 minus 1 over 5. And so what I like about this problem is there's really a more general problem lurking. And then you can ask yourself, is it easier to try to do the general problem or is it try to do something specific? What part of the 80%, the 4/5 really matters? And when you're looking at, bless you, one data point, it's not immediately clear, bless you, what matters. Okay, any other questions about this one?
It's assumed that big N is at least 1, right?
It's assumed the big N is at least 1.
So it doesn't work for 0.
Right, because he says, let's see. Well, I mean, at 0,
You go from 0 to 1.
right. So we don't consider what your free throw percentage is when you have not made any shots. But that is a good thing to be aware of. And sometimes people do forget to check various cases like that. In her first N attempts, if she's had no attempts, what would you say? Years ago, the Red Sox had a pitcher who was absolutely a disaster. And he could only be used when the game was a blowout in either direction. And they brought him in the 9th inning. The Sox were leading 10-3. Normally, when they bring in a relief pitcher, they give you the ERA. That's how many runs they allow per 9 innings. They didn't give his ERA. They just gave 3 dashes. And the reason is he had let in runs, but he'd never gotten anyone out. So his ERA was plus infinity because it was dividing by 0, and the network did not have the symbol for infinity to display. And so it's just like, we can't talk about his ERA. In a situation like this, what should we say if there were no attempts? So it's saying it's going from less than 80% to more than 80. So if you haven't taken any shots, what would you say your free throw percentage is? It's 0 divided by 0. Here's a fun one. This is an aside. 0, let me make sure I get this right, times infinity equals -1. So this is a nice result. So we'll see how much of your geometry and algebra you remember. Without loss of generality, if I give you a line, let me assume the line goes through the origin and it has slope m. I want to draw a line perpendicular to it going through the same point. What is the slope of a line perpendicular?
-1 over m.
It's -1 over m. One way to prove this is if we call this theta, this is the point cosine theta, sine theta. And then here, this is 90 degrees. And so you can use that to then figure out what the slope would be. This is why I want to have the point of intersection being the origin, and I can have the other point on the unit circle. You can prove the product of the slopes is -1. So the theorem is product of slopes equals -1. So if you think about it, whenever I have 2 perpendicular lines going through the origin, the product of the slopes is -1. What happens when you have the vertical line and the horizontal line? The slope of the vertical line is infinity. The slope of the horizontal line is 0. So if you look at the ratio, if you look at the product of the slopes, it's -1, -1, -1, -1, -1, undefined, -1, -1, -1, -1. It makes sense in this problem to say that the product of 0 and infinity is -1. All right, so just a fun aside from your comment. All right, so now let's try to do this one. Okay. And one of the things you want to be doing whenever you look at, is whenever you look at these Putnam problems or just problems in general like this, is try to figure out which things matter. Try one more time. There you go. Okay. So which number do you think matters? Which numbers matter? And they can matter to different levels. looking at this problem, when was this problem written? 2023, right? So this over here, it's the year. Probably not too important. This doesn't mean that 2023 doesn't matter. And it doesn't mean that 2023 won't come into the result, but I'm not worried about replacing 2023 with 2024 or 2021. It's unlikely that 2023 itself is playing a key role in something like this. It might, you might have an induction and you might need a certain critical value of something, and so it might be chosen like that. Which numbers do you think really matter? Zero. This matters where we're evaluating it. This is important. Any other numbers that matter? So the coefficients of x, this product, but we're going up to n. But it is that their first power is not squares or anything like that. But there is one other number. It's kind of hidden.
So the numbers. The second derivative.
Yeah, the fact that it's a second derivative. So this is the second derivative. So I would say that that's a hidden number. That this is something about the second derivative and not about the first derivative. Is anybody excited about taking the derivative of that product? But you have to remember, the goal is to get to the correct solution. It doesn't matter how you get there. One way to get there is to calculate the second derivative and then specialize to zero. Or could we just jump to what the value is at zero? So what happens when you take the derivative of a cosine? What do you get? Negative sine. And the mnemonic I like to have is negative sine minus sine. So we know the derivative of cosine is minus sine. When you evaluate that at zero, you're going to get zero. So when I take the derivative once, I'm going to get a bunch of terms that are going to be cosines, and one term will be a sine, and I'll have to look at all those possibilities. Then I take another derivative. If I don't hit the sine term, then I'm going to have two sines somewhere, and there'll be zero. So the only way that the second derivative terms are going to contribute is when both derivatives hit the same factor. So the key observation that fn double prime of 0 is going to be let's do it this way. Let's do the sum m goes from 1 to n. So I have two derivatives hitting the mth piece. So derivative of cosine is minus sine, and then derivative of minus sine is going to be minus cosine, right? But I'm going to have an m squared come down because I'm going to get it twice. So I'm going to get like a negative m squared cosine of mx. And then I'm going to have the product over all L goes from 1 to n. L does not equal m of cosine Lx. Is everybody comfortable with that? Is that when I'm taking two derivatives and evaluating things at 0, oh, and these should not be x's, these should be zeros. Right? So that makes things pretty easy. So what's that sum going to be? This is just going to be the sum. M goes from 1 to n. I'll put out a negative sign of m squared. Now, who remembers? It's n plus 1, 2n minus 1, I think. Plus 1, sorry, 2n plus 1 over 6. How can you tell if this is right? Plug in, take a few values of m. So if I take n equals 1, I'm going to get the sum of 1 squared, which is 1. And when I over here, I have 1 times 2 times 3 over 6, 1 equals 1. If I take n equals 2, I'm going to get 1 squared plus 2 squared, which is 5. And on the other side, I'm going to get 2 times 3 times 5 over 6, which is 5. You can do it a few more times, but this should be enough to convince you that we've remembered the formula correctly. So we want n such that n times n plus 1, 2n plus 1 over 6 is greater than 2023. So just find n so that n plus 1, 2n plus 1 over 6 is greater than 2023. How hard is this going to be? So we know the right-hand side is greater than n cubed. It's actually greater than 2n cubed, right? So we're trying to solve n such that n plus 1, 2n plus 1 is greater than 6 times 2023. 6 times 3 is 18, 12, 13, so 12,138, I think. But the left-hand side is greater than 2n cubed. So if 2n cubed is greater than 12,138, we're clearly okay. So if n cubed is greater than if we divide by 2, so say 600, I'll make that 1220, just to make my life a little bit easier. 6100, we're okay. And so 6100, replace with 8 times 10 cubed, I'm sorry, 2 times 10 cubed. So if n is greater than 20, we're okay. This is just like a quick estimate of how far I need to go. So I know once I get to n being 20, I'm fine. So now we just have to try a couple of values of n to figure out. Yeah, I would approximate the left-hand side with 2n cubed and just try to figure out exactly where to go. But this is a Putnam problem. We've reduced it to finding the first n such that this cubic is greater than 12,138. That's fine. We can fill up some scratch paper and multiply things without too much trouble. So the key point for this problem is to recognize what you need to compute. And the most natural instinct when you see a problem like this is to calculate the derivative. And then once you calculate the derivative, then specialize. It's much better for this problem to take a step back and realize I don't need to calculate the derivative. I only need to calculate the derivative at 0. There are other ways you could do this problem that would be a nightmare. We can write sines and cosines in terms of trig functions. And again, this is one of the nice things about this class is I get to pontificate and show things. Do you guys know how to derive all of trig in less than a minute in the exponential function? Oh, this is good. So all trig comes from the exponential function.
I think all of the element functions come from exponents or logarithms.
I mean, if you give yourself logarithms, then you can also get polynomials. So if you're willing to do exponentials of logarithms. So I'm going to assume that e to the x is 1 plus x squared over 2 factorial plus ... is the sum of x to the n over n factorial. N goes from 0 to infinity. Cosine of x is 1 minus x squared over 2 factorial plus ... is the sum, n goes from 0 to infinity, negative x squared to the n over 2n factorial. And then sine of x is x minus x cubed over 3 factorial plus dot 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 equals, I don't really want to write it. And then what you note is e to the ix is cosine x plus I sine x. This is one of the most important identities in all of mathematics. And then if I give you, you'll say z equals a plus ib, then the length of z is z times the complex conjugate of z square root, which is going to be a squared plus b squared square root, with z bar equals a minus ib. Everybody comfortable with all this? Okay, so now let's get all trig. E to the ix times e to the minus ix, what does that equal? One. And it also equals cosine x plus I sine x times cosine x minus I sine x. So I'm using the fact that the sign of negative x, so using the cosine of negative x is equal to cosine of x, and the sine of minus x is minus sine of x. Therefore, 1 is cosine squared x plus sine squared x, and the imaginary parts cancel. That's Pythagoras. We just got Pythagoras. E to the ix times e to the I y is e to the I x plus y. So cosine x plus I sine x times cosine y plus I sine y is equal to cosine x plus y plus I sine x plus y. When we expand things out, we get cosine x cosine y minus sine x sine y plus I times sine x cosine y plus cosine x sine y. So this part over here equals that. This part over here, there's your angle addition formulas. The angle addition formulas for sine and cosine are inherited from the formulas for the exponential. There's a lot more we can say. The most important limit in differential trigonometry is the derivative of sine at 0. And that's the one from all trig falls from there, because we can use these angle addition formulas. So if we can find the derivative at one point, we can find the derivative anywhere. Have people seen this? Do people want to see this? All right. If I want to find sine prime of x, that's the limit as h goes to 0 of sine of x plus h minus the sine of x over h. And that's going to be, the limit as h goes to 0, sine x cosine h plus cosine x sine of h minus sine of x over h. It's the limit as h goes to 0, and then we'll have we have two sine x's, so I can pull a sine x outside the limit, and I'll have cosine of h minus 1 over h plus the limit as h goes to 0 of, I pull out a cosine x here. And then I'll have sine of h over h. So is everybody comfortable with this? I'm using the limit of a sum is the sum of the limits, but how can I write 1? I have cosine h minus 1 over h. How should I write 1? So much of math is pattern recognition. That's why I love this problem. So I want to write 1 in terms of cosine. How should I write 1 in terms of cosine? It's not cosine of h, cosine of. How do I get 1 using cosine?
Cosine of 0.
Cosine of 0.
You can't say h.
Cosine of 0 plus h minus cosine of 0 over h. How should I write the second factor? I should write it as the sine of 0 plus h minus the sine of 0. This is cosine prime of 0. This is sine prime of 0. We just showed that if you want to find the derivative of sine anywhere, you just need to know the derivative of sine and cosine at 0. The same argument holds for cosine.
Why can we do negative sine of 0?
What's the sine of 0?
Yeah. Okay.
It's 0. So I'm adding 0 in a clever way. So now we just need to figure out what's the derivative of sine and cosine. If you're willing to consider that we know sine squared x plus cosine squared x equals 1, if we take the derivative, we get 2 sine of x sine prime of x plus 2 cosine x cosine prime of x equals 0. What's a good choice to take for x? What would be a good choice to take for x in this formula? It's true for all values of x. What would be a good choice? 0. Because we just showed in the previous slide that we need to know the derivative of sine and cosine 0. So we get 2 sine of 0 sine prime of 0 plus 2 cosine of 0 cosine prime of 0 equals 0. Sine of 0 is 0. Cosine of 0 is 1. Therefore, we get 2 cosine prime of 0 equals 0. Therefore, cosine prime of 0 equals 0. It turns out cosine prime of 0 is easy to compute. And again, this is a point that is glossed over, I think, in almost every introductory class. The reason it's easy to compute is because it's 0. Sine is hard to compute because its value is not 0 when you do sine prime of 0. You actually get a different answer depending on how you measure angles. This is one of the reasons we use radians, because when you use radians, now the derivative of cosine is minus sine, and the derivative of sine is cosine. This is why we use radians. So radians make sine prime of 0 equal to 1. That's another way of looking at why we made that choice. So there's a lot of really good stuff lurking in the background for this problem. For the last bit today, I want to talk about a problem my son and I came up with. The reverse tic-tac-toe. And so one of my former students just said he wants to try to code this. He's learning how to code right now. So in standard tic-tac-toe, whoever gets 3 in a row wins. In reverse tic-tac-toe or toe-tac-tip, which I'm trying to get people to like, you win if you make the other person get 3 in a row. Instinct. Do you want to go first or second? Gut feeling. You want to go second because you win if the other person gets 3 in a row. You probably don't want to be the first one putting. That's not a proof, but my gut feeling is you're right. I would much rather go second. So how many opening moves do I have? I have 9, but up to symmetry, I have 3. Right? By symmetry, oops. These are all the same. The corners are the same, the middles are the same, and the center is the same. So there's 3 moves up to symmetry. So when we're analyzing the game, there's not that many possibilities. If you're going first, which move do you think you want to avoid like the plague? Probably the center, right? Because the center has the most ways of getting 3 in a row. That doesn't mean that this is the right thing to do. Sometimes it's better to take a local hit for a global gain. But again, my gut instinct, if I had never really thought about this game and I'm going first, I don't want to go in the center. What is your goal when you're playing this? There's 2 acceptable goals. To win, good. To win is one natural goal, and what's the other natural goal? Not to lose. They're not equivalent. It's possible for the game to be a tie. I know nobody ever makes illegal bets on things like March Madness and basketball and stuff like this. But sometimes people, either they have money down or they have their pride down. And a lot of people, they know they're not going to win. They just don't want to be last. So their goal is not necessarily to win. It's to avoid being humiliated, to have a bracket that looks reasonable. So one possibility is you might play to just guarantee yourself a tie. That's a lot easier to analyze than guaranteeing. So do you want to go first or second? Second. All right. So I'll let you go first. Where would you like to go? I never said I'd listen to your wishes. Okay. So without loss of generality, you will take the upper corner. And I just want to explore a strategy right now to see how it does. I'm going to mirror image you. And so I will take the corner over here. So whatever you do, I'm going to mirror image. And I'll put subscripts so we know the order of the moves. So where would you like to go now? You could, of course, stop my strategy by taking the center. It's okay if you don't make the. Where would you like to go right now?
Adjacent middle.
Adjacent middle. And again, because of symmetry, I can choose either adjacent middle. So now if you go there, is there any way for me to keep up the symmetry? Would going down here be what I should be doing to keep up the symmetry? No. Okay, that's not the symmetry. That's not keeping it symmetric.
I think you're winning here because you force us to.
Well, I'm saying if I go there, is that keeping the move symmetric? I mean,
Well, what's the diagonal?
to me, it looks like it's keeping it symmetric about this diagonal. I would say that if I'm playing a symmetric strategy, this is at least justifiable as a symmetric move. So now, where would you go?
If we know you're going to be playing symmetrically, then I might go to the top middle.
So if you go
I think this
top,
is false.
so if you go top middle,
Yeah.
then you're in real trouble because you've got you've got 2 different ways of getting 3 in a row. I will go symmetrically down here, and now of the squares that are left, 2 of them give you wins, 2 of them give me moves, but you have to take 2 out of 3 moves.
You don't just go center and then move it.
So now if you go center, however, then I lose.
Yeah.
And so then at this point, yes. So if you now stop doing that, and now this is where you did a strategy up until a certain point, and now you take the middle. And now I would lose. And so that would be 08. And I've lost. This is why it's so great to get some data and play with some small things by hand. I think symmetric responses is a reasonable strategy. But what you can do is you can lay a trap. And yes, you will have to get one of the 2 corners, but I will have to get a corner first because you chose the middle. And order matters. So who do you think had the advantage, player 1 or player 2? So player 1 has the extra piece on the board, but player 1 might be able to move you into a certain direction. And this is why it's sometimes not immediately clear which is better. So I'm going to end with a research project that I've looked at with many of my students. So these are called MSTDs. These are not bad to get. These are more sums than differences sets. And so you take S to be a finite set of non-negative integers. And we're going to form two new sets. The first is the sum set, S plus S, and it's going to be all sums of the form X plus Y, where X and Y are in S. And then we'll have the difference set, which will be S minus S, which will be all things X minus Y, where X and Y are in S. So we can compare the cardinalities. Which set is larger? And so if I look at random sets of integers, do you expect the sum set to be larger? Do you expect the difference set to be larger? Do you expect them to have the same size? You can give me a nice reason why the sum set should be larger. You can give me a nice reason why the difference set should be larger. So can you give me a reason why the difference set might be larger?
Difference of, positive and negative.
You can have positive and negative, as the pair xy gives x minus y and y minus x versus just one x plus y. So a generic pair gives you two differences but only one sum. Why might the sum set be larger? So this was a generic pair xy. What's a non-generic pair? So I chose two elements x and y. Instead of choosing two elements x and y, I choose one element. Because if I now, as the pair xx gives 0, which is x minus x, but 2x for the sum. So all the diagonal elements will always give you new sums. And all the diagonal elements will always give you the same difference of 0. So this is one reason why the sum set could be larger. This is one reason why the difference set could be larger. At times, it's not clear which is going to win out. We saw this with the egg drop problem where the solution was to equalize the two. And so here, this is just a game that I will let you ponder. And I do not know the answer yet as to, is there a winning strategy for reverse tic-tac-toe? Is there a strategy that will at least protect you from losing? So those are the two questions. Can you guarantee a draw? And can you guarantee a win? All right. So this is a good place to stop.